Hello everybody, Alison Raby here from the University of Plymouth. And Eve and I are kind of co-facilitating this also with Professor Dina Diala from University College London. Eve was going to give a welcome. She was going to say the number of participants. I think we're down to 53, and that might be in addition to the panelists. We're hoping that more are watching live stream on YouTube, if that has worked. Bit of housekeeping, the microphones and videos will be off for participants. For panelists, obviously they will go live when they give their presentations. Please feel free to use the Q&A button, and we'll have questions after individual presenters if we've got time. Otherwise we'll pick them up in the discussion. And I think that's all that Eve was going to say. I think I can just see a chat, just make sure it's not Eve. Okay, so that's fine. So over to me then. So I just need to put that into display mode and share my screen. I'm hoping that people can see the screen now. Okay, so I've lost my notes, but I think I can remember what I was saying. Let me just see whether I can just try and get my notes up separately. I was the only person not able to test out their presentation in advance. Well, I'll wing it. I think I remember what I was going to say. So let me just get the Zoom window up to make sure that no one's trying to get hold of me and saying, Alison, we can see something dreadful in the background. Okay, just increase the size of that so I get the instructions at the bottom. No, I can't see that, but perhaps if anything untoward happens and somebody could, one of the panelists could just appear and sort of motion to me, because I can't actually see anything apart from my slide now. Okay, so thank you all for joining us. The purpose of today's meeting is to really celebrate the STORMLAMP project. It's now ending. It was funded by EPSRC, and we wanted to say a big thank you to all of the participants and all of those who were former members of the STORMLAMP project, but those in the background, people who've shared the material with us, people who have reviewed some of the work. So that's been a really welcome part. But we didn't just want to talk about the STORMLAMP project this afternoon. We also wanted to give an opportunity to show some of the other not actually related projects, but things that have been going on in parallel, just coincidentally. And so we've got 6 great speakers lined up this afternoon. I hope that you can have a really enjoyable time in this this workshop. Mostly presenting on lighthouses, but we also have some conventional coastal structures, and we've also got something on more contemporary structures with wind turbines. But to briefly set the scene, our association with lighthouses started nearly 10 years ago. Trinity House contacted the University of Plymouth, and they were concerned about the wave loads on the rock towers with climate change and predictions into the future. And so we started off doing some very simple laboratory modelling. And then following that, we monitored the Eddystone Lighthouse, which is situated very close to the University of Plymouth. And we put some geophones to measure the structural response, but also some downward pointing cameras as well. And that initial pilot project showed that actually the structural vibrations were very limited, so of fractions of a millimetre. We did a structural model with the Politecnico di Torino in in Italy. It was a simple finite element model. And what we found was that the geophone data didn't quite match up to the finite element model data. The geophone data showed something at 8 Hertz that wasn't visible in the actual. We measured it, but we couldn't numerically simulate it. So that led on to a much more comprehensive project called STORMLAMP that started about 4 years ago. And we extended the project to include a field campaign led by University of Exeter, University College London, where they did much more comprehensive structural modelling. And obviously we brought to the table the hydrodynamic modelling that we do at the University of Plymouth. So you can see some laboratory modelling here, some computational fluid dynamics modelling here. And we also looked at some long-term statistical projections to try and work out what the wave loading would be. That wave loading was provided to the structural model, which in turn had been validated by modal testing. So in fact, the first step was to do modal testing of 7 rock lighthouses in the UK and in Ireland. And Wolf Rock and the Fastnet Rock also were the subjects of a long-term monitoring campaign. The Wolf Rock Lighthouse revealed some structural vibrations that were equivalent to earthquakes in storm conditions. And the Fastnet Rock Lighthouse, that actually had much more modest vibrations because it's higher up out of the water and because it's a much more massive structure. We are now producing a guidance note for the UK and Irish General Lighthouse authorities. That information will also potentially be of use to others involved in marine structures. If you'd like to know more about the STORMLAMP project, then we do have a really comprehensive website, stormlamp.org.uk. On that, there's a series of blogs, there's videos, there are links to all of our publications. So that's a huge repository of information that you can dip into. We also fairly recently edited a special issue of the Philosophical Transactions of the Royal Society, where we brought together information from lots of different lighthouse projects and also other heritage structures. And I think that some of the people on this call were contributors to that, so thank you very much. Okay, so that was by way of introduction. I'm not sure whether I said everything I had in my notes. Hopefully I did. Introducing the first speaker then, so we have Tom Nancollas. So Tom, from memory, is a historian and conservationist, and he has recently published a delightful book about the Seashaken Towers, and his presentation will describe the process of writing that book. So I'm just going to try to stop sharing my screen now, and then I will pass on to Tom.
Thank you, Alison, and thank you for a great introduction to the day and to the project. I'm really excited to hear the speakers we have lined up. And this already looks like such a fascinating amount of data and really sort of important findings for the towers going forward. I will just share my screen seamlessly, hopefully. Mm-hmm. Okay, well, hi everyone, good afternoon. It's a delight to be here with you today, and as I say, a really exciting series of speakers lined up. Can't wait to hear what they have to tell us. But I thought I'd set the scene first of all with a few reflections on these buildings as heritage, really. My background is that of building conservationist, as Alison mentioned. And that really involves the appraisal and kind of consideration of significance in buildings and places. What makes them special, what makes them really important in relation to our current times, but also to our history as a nation. And my job really involves sort of identifying and protecting that significance when there are proposals for change or proposals for repair. And I'll just give you 2 examples. One of my earlier jobs for English Heritage was dealing with church grants, so repairing inner city London churches. My current project for the City of London is to help with the move from the Museum of London from its site in the Barbican to the vacant buildings at Smithfield Market, Victorian structure, and the post-war poultry market. So it's really interesting, mostly land-based stuff. And I got into lighthouses, or became interested in them because I was qualifying as a building conservationist, doing my master's degree at Kingston University, and wanted to really kind of explore the most extreme form of heritage that we have in this country. And, you know, what fits the bill better than the rock lighthouse? You know, obviously, first and foremost, an aid to navigation, but they are also very much historic buildings. And they have an architectural uniqueness which gripped me from the off. So the book is called Seashaken Houses because there's a poem by Dylan Thomas and his prologue to his collected works in 1952. He uses the phrase of his boathouse, which you can see here, in my sea-shaken house on a breakneck of rocks. Now this illustrates quite nicely the sort of the divergence that rock towers have from buildings on land, you know, traditional buildings on land. His boathouse here is very much an ordinary building with 4 walls and a roof, you know, nothing especially sea-shaken about it. But when we compare it with the Wolf Rock Lighthouse shown in this picture, we do see the difference. And this is truly a sea-shaken house. For those on the call or watching on YouTube who are perhaps unfamiliar with the basics, there are 20 of these towers still standing in the seas around Britain and Ireland, of a total of 27 that were ever constructed. The first was constructed in 1698, the last in 1904. So we have sort of 4 centuries really of innovation, audacity, experimentation, and most importantly of all, inhabitation at the extremes of the country. And you know, the stories of these buildings as architecture, their developments in civil engineering and the design responses to the sea are as extraordinary as the fact that people lived in them for 400 years. Ending with the automation of them in the 80s and 90s. So my book, Seashaken Houses, really seeks to draw out these myriad strands of the story for the general reader. I would also say that Seashaken Houses was finished, the writing process, in 2017. So I overlapped with STORMLAMP only a little bit, but I was really inspired by what I saw at the start of this project. And, you know, I think we come from the same place, ultimately, which is a fascination of how on earth these structures take such punishment. Just a quick note on the reason for their existence. Britain is a seafaring nation, always has been to greater or lesser extents, and consequently shipwreck has always been a pretty visceral fear. One of the earliest shipwrecks, recorded shipwrecks, the White Ship of 1120 AD, really shows the catastrophic consequences that shipwreck can have. This was an episode in which the then heir to the throne, Prince William, was lost at sea in the White Ship when returning to England after a peace treaty was concluded in Normandy. This prompted a succession war, followed by a civil war that lasted for decades. So it just goes to show the power that an unnamed, unmarked, submerged rock has in the affairs of the land. And then moving on through British history, you know, economically, ships and their cargoes were of increasing importance. So the consequences of shipwreck and of, you know, high volumes of shipwreck were not just human and tragic, but also economic. And for a nation which really relied upon maritime trade, especially the boom of the 18th and 19th centuries, it became more important than ever to safely light the seas. So here we have the first in Britain, the famous Eddystone. Now, I know many of you won't need an introduction to this remarkable lighthouse, but I want to show this image. This is the first ever rock lighthouse, designed by a man called Henry Winstanley, and built in 1698, lasted until 1703, when it was blown away in the Great Storm. The point about it really is that it worked. It survived 4 sets of winter gales, albeit with strengthening, and may well have stood for much longer had it not been for the worst storm the country had then known at the time. I also want to make the point, I'm also fascinated here by the fact that these prototypes were in many ways our first architectural responses to the sea, so they have a kind of uniqueness. There was no precedent that the engineers really had to go on. And Henry Winstanley here, as you can see, designed quite a bizarre tower, which looks more like a sort of Renaissance corner tower than it does a sort of serious and chaste aid to navigation. And this man, incidentally, Winstanley, was a rather superb and flamboyant showman, jack of all trades, typical creature of the Renaissance, really, the Restoration, sorry. So in many ways, it's perhaps fitting that he was blown away when inside it when the tower was felled. So following these prototypes, as I say, many of which survived, the blueprint was found here on the Eddystone again by John Smeaton. We've touched already on the Eddystone, of course, but I just wanted to briefly highlight the principles of this successful blueprint, the tapering tower with its low centre of gravity, its entire masonry construction, and of course the dovetailed stonework, which for me really does reveal how far apart from land these buildings are, not just in distance, but also in design and in construction techniques. There are dovetailed masonry structures on land, but they don't have to put up with anything like the wave loading of the rock lighthouses. And the intricacy and the ingenuity of the dovetailed stonework here, designed by Smeaton, for me really kind of embodies their architectural uniqueness, their otherness. This was a formula that would be used in the majority of the subsequent rock lighthouses around Britain. Incidentally as well, during the research for my book, I did discover that one of my ancestors actually worked on this tower and the deconstruction of it in the late 1870s, which was a very strange thing to find out. So we have the masonry carcasses of these extraordinary buildings, but I want to make the point, and we see this with the next of them to be constructed in the Eddystone fashion, the Bell Rock in the North Sea in 1811. These were not just functional works of engineering. These were also buildings with fully thought out interiors. They were designed not just to show lights, but to house the men and equipment which operated them. And consequently, you have these very interesting interiors in such remote locations. And perhaps the strangest of them all was the Stranger's Room in the Bell Rock, designed as a sort of visitor's room and library. And as you can see from this watercolour painted in 1865, it was as fine as anything in the Edinburgh New Town. It had a Turkish carpet, imitation plasterwork ceiling, fine carpentry and cabinetry, a marble window surround, and even furniture bought from an Edinburgh boutique. For me, this says a lot about the attitudes of the age, that such a room was felt necessary 11 miles offshore. And you can also see, in a way, Robert Stevenson, the engineer's efforts to sort of align this building with the best of the architecture that could be seen on land. And it is perhaps a comment on our own age that in the late 20th century, this room was completely removed as part of the modernization of the tower. It no longer exists. We have a lost interior here. Of course, these buildings, with their interiors, were inhabited for 400 years, as I say. This is the Bishop Rock Lighthouse off the coast of the Scilly Isles, but also off the coast of Land's End. And perhaps there has never been a job where there has been a stranger mix of the extraordinary and the ordinary. Here we have the keepers ascending to their place of work from their small boat, tossing precariously upon the waves down below. Their jobs, now gone in Britain, of course, were this peculiar mix of the mundane and the strange. They were quite a very sort of specific breed of person, and the circular shifts that they lived day in, day out, and the circular environments in which they moved, and the circular furniture, the circular rooms, etc., were all kind of a piece with the building. And you can see building and operators almost as working together as a kind of machine. A machine for living in is one way of looking at these things. And I would make the point too that they were designed to be lived in. They were designed to be inhabited. And from a sort of conservation point of view, when a building becomes vacant, that raises questions about its future. I mean, these buildings are still very much fully functioning and vital aids to navigation, of course. But their vacancy now means they operate differently. They were designed to be regularly ventilated, heated and cooled, swept out, and just generally cared for on a day-to-day basis in a way that now doesn't happen. So there's that question about, their fabric and their interiors. Also, the alterations required to achieve this different method of operation have resulted in changes to the structures themselves, and perhaps the most poignant are these door bolts added to the door of the Fastnet lighthouse. During the automation of that tower, it was realized that this particular entrance door was never designed to be locked from the outside, because it was always assumed that there would be someone within the tower permanently there to greet the visitor. And the phrase unwatched is used of the automated rock towers and lighthouses, and that's significant, I think, in several senses. The unwatched in the sense that there is no longer a physical human being inside the tower watching the light. More widely, I think it reflects the way that the sea itself is now, rather unwatched by us as a nation, despite still being the source of most of what we own and what we buy. So it is quite a poignant comment, I think, on the way our relationship with the sea today, and that's something I tried to draw out in the book. Just conscious of time, I wanted to quickly walk you through a couple of lighthouses I visited as part of the book's research. Now, I wanted to, of course, treat the famous rock towers, the Eddystone, the Bell Rock, the Fastnet, but I wanted to also explore these other, quite lesser known towers and bring them into the story, because they really do reveal how variable and how, in a way, individual these otherwise homogeneous structures are. So Hall Bolin is quite an interesting one. It doesn't appear very much in the literature around rock lighthouses, and I think part of that is to do with the fact it stands not out in the open sea as such, but just inside the Carlingford Loch between Northern Ireland and the Republic. It's actually a very early tower, completed in 1824, so it was the next, in fact, after the Bell Rock was finished, and it is a sort of vernacular version, a vernacular copy of that celebrated lighthouse. The entrance to the Carlingford Loch is very hazardous, reef-strewn, and so it was built in this sort of rock tower form, even though it's not quite out in the open sea. The architect, George Halpin, almost nothing is known about, and we consequently have no drawings or really any original documents relating to this lighthouse, at least that I was able to find, only later paperwork. And in fact, quite interestingly, most of that paperwork relates to the fact that it stood on the border of Northern Ireland and Republic during the Troubles and was used as an orientation point, and was in fact at one point raided by the Royal Marines. So it does have a slightly more eventful history than most towers in that sense.
2 minutes, please, 2 minutes.
Sorry? Oh, thank you. Yes, so 2 minutes. This is the interior of the tower. It was one of the first to be automated in the 1960s. So you can see the sort of the level of decay and weathering that the interior has undergone. Just quickly now, Perch Rock. This is the another early tower built in 1830, just outside the entrance to the Mersey. In fact, so close to New Brighton Beach as a result of various changes to the shoreline there that you can walk to it at low tide, and that is what I did. I waded across through this bowl of water and up the ladder. Now, this is one of this is privately owned, this tower, and it is one of two of the rock lighthouses that doesn't shine a light today. Nevertheless, it is fascinating because it's virtually a copy of the Eddystone, Smeaton's Eddystone, with a few design tweaks at balcony level. Designed by John Foster Jr., who was perhaps more at home with the grand classical buildings he was then constructing in Liverpool. But the remarkable thing about this one is the late Georgian interior is pretty much unaltered, and you can see all of the fairly humble sort of carpentry and cabinetry, stair compartment and ladders in this photo. The bunks are not the true banana bunks, but they are more segmental, like a segment of an orange, and I can say from experience that they are hellishly uncomfortable. I spent a night in this tower in February 2016 to try and get under the building's skin. You can see also the cast iron pipe that used to carry the chains and weights of the clockwork mechanism turning the light, and that mechanism does still survive in situ, which is quite rare for rock lighthouses. Finally, the Fastnet. You'll all be well aware of this tower, and so I won't go into too much detail, except to observe that as a building, it is perhaps one of the most flawlessly constructed things that I've ever come across as a building conservationist. 100 years on, it's still pretty much as it was built, as far as I can tell, with subsequent alterations, obviously, around the power source and the light. That is the original apparatus, incidentally, revolving majestically in the lantern room. An immense amount of care and thought went into this tower, and you can see that from the left-hand picture with the little notch cut into the lintel above the window to receive the shutter bolt. Thoughtful little flourish, and hardly an inch of the lighthouse does not have some thoughtful element like this. I also wanted to quickly point out the network of copper pipes on the right-hand side picture, which is obviously a later addition. But for me, as a conservationist, we're about telling the stories of buildings like this as historic buildings. This is another layer in its story, it's another chapter, and is also a fairly superbly worked piece of craftsmanship. And so I would make the point that if this tower ever is solarized as is proposed And it would be a shame to remove these other layers of its history, because they do form part of its significance, I believe. The Fastnet, of course, is also famous for its mosaic floors, which is to be found at some levels of the building. Here you can see these rather stylized fan patterns, which I think resemble the waves, or an artistic rendering of the waves that surround it. And that makes the point again that, you know, these are not just functional structures. They had interiors that displayed a great deal of pride and thought on the part of their builders. So that's just a quick trot through some reflections on these buildings as heritage, as part of our built heritage, albeit in extreme form. And I would end by just saying that, you know, they continue to be vital, functioning pieces of our aid to navigation sort of network. But I think they also now act as monuments to the great seafaring heritage that Britain has. You know, there are very few, you know, traces of this massive amount of history out upon the waves, except these permanent towers. So that is what I tried to convey in Seashaken Houses, and I hope you enjoyed what I had to say. I'm available for any questions, as Alison said, and I'm looking forward to the rest of the talks. So thank you very much, all.
Thank you very much, Tom. That was a really interesting presentation. And, you know, I'm just very familiar with the engineering aspects, but so good to hear about the historical and conservation aspects. Our STORMLAMP team are well familiar with the Fastnet Lighthouse after an unplanned 1 week stay there when they were deploying equipment, doing testing, and the weather changed and they got stranded there for rather longer than they'd anticipated.
Yeah, wonderful. I think actually the same chap who took me out there, Neely, I think also accompanied your team.
Right.
And so, yeah, we reflected upon the hazards of the weather. I must say the Commissioners of Irish Lights were very, very generous with their time in that respect. Yes.
Okay, so thank you very much, Tom. So we've just we'll pick up any questions and answers at the end. Apparently, sorry, I spoke slightly out of turn earlier.
That's fine,
so
no problem.
if you've got any questions, then we'll pick them up at the end. So the next contributor is Rob Dorey. So Rob Dorey is representing Trinity House and also potentially the wider UK and Irish General Lighthouse authorities. Rob's going to be speaking on why STORMLAMP's research is important to the UK and Irish GLAs. So Rob, if you would like to share your screen and give your presentation.
Hello, Alison. Yeah, thank you very much. Hopefully hopefully you've got my my slide up in front of you. Okay, so thank you, Alison. So my name's Robert Dorey. I'm the Operations Director for Trinity House. I'm a mariner at heart and a background of life at sea. I'm the user of the services and very much value, therefore, the service that they offer in terms of safety at sea and for the safe flow of trade around our shores and into and out of our ports. For those less familiar, Trinity House is one of the 3 general lighthouse authorities, which along with Northern Lighthouse Board and Irish Lights cover the statutory responsibilities for the provision of aids to navigation and responding to wrecks and new dangers around the coasts of the UK and Ireland. And although individual GLAs, as we call ourselves, have their own areas of responsibility, Trinity House for England, Wales, the Channel Islands and Gibraltar, Northern Lighthouse Board for Scotland and the Isle of Man, and Irish Lights for the entire island of Ireland, we do work very closely together, and we have established arrangements for the sharing of technical knowledge and operational experience, while also sharing our GLA research department known as GRAD, led by Martin Bransby. We operate some shared contracts and ensure that resources are utilised collectively where required to cover the risks within our combined waters. So although the geography of our regions varies, as does the nature of the seabed, the ports and nature and density of shipping in different areas, we also have a considerable amount of commonality across our estates. Many of our lighthouses were built around the same era, and although there are some very modern structures, there are many built in the 1800s, and a number of these are offshore or fall into the category that we call rock stations. And perhaps I'll just pick up on Tom's previous point of unwatched at this moment, because from our operational perspective, they're monitored very closely from ashore for Trinity House in our 24/7 monitoring centre in Harwich, where we at any time can make sure we understand the operation of the light, any hazard warning signal, the condition of batteries, intruder alarms, and so on. So perhaps I'd offer watched from afar rather than unwatched. But our interest in this is really quite simple. These structures have been around for 150 to nearly 200 years in some cases. Can we assume that they will be there for another 200 or more? That's really where we sort of come from in this respect. Have the additions such as lantern top helicopter decks altered the way in which they behave, or an enhanced or weakened the structure? Looking further ahead, what would be the impact of rising sea levels and more frequent and more extreme weather? Given the nature of the environment which they endure, as the photo here depicts with Longship's light, this is significantly more challenging than a land-based station. We should also not lose the sight of the fact that these are operational structures. They're not museums. They do undoubtedly contain a significant amount of history. But we're not museums, and we need to keep them operational. We therefore need to have a far greater understanding of our structures so that well-informed investment decisions can be taken to ensure that we can still deliver the safety service required of us into the future. In our view, STORMLAMP has been a significant world-leading research project with detailed analytical assessment, including modal testing, computational fluid dynamics, and structural engineering analysis on masonry structures in an ever-changing marine environment. Because the work was so detailed and highly technical, using the expertise from the 3 universities, it has proven to be of great value. As a result, there is now a far greater understanding of the behaviour of our structures, especially in the sort of extreme wave loading conditions, which may be more prevalent in the future with the impact of climate change. The interaction of the 3 universities brought with it a range of highly technical competencies, which the GLAs would not normally have been able to access either through our own staff or via marine engineering consultancies in the sector. This highly valuable, detailed and technical work was possible because of collaboration of experts from different fields. The STORMLAMP results will be of significant value, not only to the UK and Irish GLAs, but through IALA, the International Association of Marine Aids to Navigation Lighthouse Authorities, and through those to our colleagues and partners around the world. I think we can all still marvel at the innovation of the original engineering teams who built these lighthouses, especially their design and construction techniques and their use of interlocking blocks. But now, in 2020, it's been possible to demonstrate just how good their structural engineering foresight was by using the latest and modern cutting-edge research techniques. So whilst the STORMLAMP project undertook detailed research and analysis into 2 towers specifically, Wolf Rock and Fastnet, the next steps perhaps might include continuing the work to develop a simplified assessment tool for assessing whether wave-washed lighthouses for assessing other wave-washed lighthouses, which could be really valuable outcome for the GLAs and other lighthouse authorities around the world in the longer term. Alison, that concludes my piece. Thank you.
Thank you very much, Rob. Okay, thank you for your kind words on the STORMLAMP project. We've really enjoyed working with Trinity House and the other UK and Irish lighthouse authorities. And we're going to be hearing actually from some of the French lighthouse authorities a little bit later, but really helpful to have that context from UK and Ireland. Thank you for that presentation. Okay, so the next presenter, Eve was going to do this, but her internet connection is not great, so I'm just doing the intros as well. So our next speaker up is Professor Dina Diarra from UCL, who was one of the key partners of STORMLAMP. So Dina, over to you for your presentation. Dina, can you hear me?
Thank you, Alison, and I'm trying to share my screen without the presentation starting too fastly, so just a second. You should be able to see it now, possibly. There we are. So I couldn't ask for a better introduction than the previous two talks to the talks that I am going to provide. And in particular, I now feel the weight of having to talk about the STORMLAMP. The main issue here is we have spent the past years in trying to put together the puzzles of how these are affected by extreme wave action. And we here we can see in the four shots here of lighthouses in the both in Britain and in France, what is the effect of waves on lighthouses. And this, of course, with climate change, as we have already heard, might become even more of an issue in the future. So without further ado, if I manage to page down this, yes, I will introduce very briefly the project that Alison had already mentioned. So what are the parts of the puzzles? The 6 lighthouses from the 19th century, designed by the Douglas and Walker. We had to determine the waves, and the groups of Bristol used both statistical stream wave theory and physical modeling, as we have heard in the ocean bases, and numerical modeling in order to quantify the waves. We had on-site investigations carried out mainly by Exeter University to determine the structural and dynamic behavior, which is fundamental to the structural analysis of the of such houses. So, however, the behavior of the lighthouses cannot be understood without understanding, without actually looking at Smithon Eddystones. So the concave elliptic frustrum, the anchorage to the base rock by way of iron bars, the stone blocks shaped and interlocked with dovetails, as we have already heard, and the vertical marble dowels and tree nails, which allow to locate each single stones in its perfect location and place. And we need to understand the ingenuity of Smithon in relation to the fact that for 150 years, there have been failed attempts before him to build lighthouses on rock at sea, and the fact that this particular one then survived for 150 more years. But let's go back to the lighthouses that were the object of our interest. So these were built in the 19th century by first Walker and then the Douglas family, father and sons, and they largely follow the prototype by Smithon, but modified the design to make the stone blocks preparation and construction on site more efficient and robust. The wealth of archival information that we have both through Trinity House and through the historic record at ICE allow us to build a very detailed model of the lighthouse, so 3D CAD models, where we have been able to actually shape each single stone, both with their horizontal and vertical dovetailing. When deciding the realization of the structural model, however, we had to make some strategic decision. And the first one was to actually choose a particular type of software that provides ability to model the discontinuous nature of the dry stonework. But also, very importantly, we decided to concentrate on the vertical keying, the vertical dovetailing, because this was most important to the behavior of the structures, as we will see in a minute. So the waves was then simulated through using Winky Umeraci theoretical model for plunging wave. And we can in that way determine for a 250 return periods, for instance, the maximum force and the length of impact of that force that, as you can see here, is in the hundreds of seconds, while the force is of the same order of magnitude of the weight of the lighthouse, and the position of the impact height. So these two information gives us enough to understand what are the possible failure mechanisms, overturning or sliding of the lighthouse. And this was already identified by Douglas in his memoirs published by the IC proceeding in 1884. So in the following, because the sliding is prevented from this vertical key that I've just mentioned earlier, we will concentrate mainly on the rocking. And Tom Dorey earlier on referred to a simplified method in order to determine when the rocking would occur. And we can imagine that the rocking will can be stimulated as something like this. And we can have a very simple method that are limit analysis that allow us to determine the line, the blue line in these pictures, which identifies the area that is safe from the area in which uplift will take place, and hence rocking is expected. So these are the combination of force and height of application which will provide that type of rocking. However, when the rocking starts occurring, then it will not be as simple as the model that we have defined for the uplift. The lighthouse will break in several portions which will rock with respect to each other. It doesn't really break because the oscillations are small, as we will see in a minute, but what matters is that there will be several portions, and this is very difficult to model. However, our simple model allows us to determine a curve of safety, let's call it, for each of the lighthouses. But most importantly, if we adimensionalize the impact, the height of impact with respect to the height of the lighthouse and the force with the weight of the lighthouse for each lighthouse, and here we are looking at Wolf Rock and Les Sanois, we obtained that those two curves that I showed earlier, they actually coincide, which indicates that basically all the lighthouses were designed to the same principles, and that we can use this principle to assess the whole family with very little diversion. And given a particular wave, this is the one that we have computed earlier, the distance from the curve will tell us how at risk the lighthouse might be from rocking. But as I said earlier, in order to really understand what's going on, we need to look at a detailed model. And here you can see two videos where we can actually properly simulate the opening of the joints. And many joints will open over a quite considerable height. And as you can see, there will be both joints on the leeward side and on the windward side that will open during the oscillations. So if we then, what we can then understand from this discrete element modeling, here we are looking at the results from the side of the leeward side. During the impact duration, the top has actually a negative movement in reverse, as can be shown by this first model. But once the impact completes, then the oscillation is the opposite one, and we have a maximum lateral displacement of 23 centimeters over a height of 35 meters. So we need to keep this in context, although it's not a modest displacement. It's basically the size of your laptop screen. what does that mean? It is a problem. In reality, what we also see is that when there is only one major oscillation of these types, and then the following oscillations are substantially reduced at 4 centimeters. So much of the energy that has been transferred by the wave is dissipated in the friction and the rocking and the contacts between the stones themselves. How does climatic change affect the structure? This was one of the questions that Trinity House posed to us to start with at the beginning of the project. So what we have done here, we have recalculated the wave in considering sea level rise, and we obtain a wave that is slightly stronger in impact force, but of slightly shorter duration, and applied also at a slightly higher height. What is the results of this? We see that if we sum up all the joints opening that I've shown before, in the presence of sea level rise, we will have a 20% increase of the actual total opening. So although the waves will not be very different, their characteristics, as you can see, it's sufficient to create a 20% difference in effect, which is quite worrying. So will these lighthouses be safe? Any single joints, we can see that the maximum opening of the joint is of the order, whether with or without sea level, it's of the order of 23 to 24 millimeters opening. And if we look at the famous vertical key that I mentioned earlier, these were designed to be 76 millimeter deep, which means that we have roughly a factor of 3 in safety, i.e. it is true that the joint will rock to each other, but none of them will be able to climb over the underward key and hence to slide off and create a real collapse. Of course, as a result of the rocking, we might have minor damage. So in conclusion, the use of the historic information to build accurate advanced numerical model, it was fundamental. However, of course, many uncertainty remains about the wave action and the way in which we quantify it. The vertical keys are, as I've shown, fundamental to explain the behavior of the lighthouses, but also their reliability, integrity, and their survival for the past 150 years. Limit analysis is useful to predict the threshold of intense rocking, and when adimensionalized can be generalized to the whole family of lighthouses. This means that the Douglas had a very good understanding of the relevant importance of the different design parameters, because each lighthouse is slightly different from the previous one, and it's particularly adapted to its to the rocking formation on which it's built. So although they are not the same, but they were really designed with the same principle. And this, for engineers, is such a wonderful thought to hold. There is substantial energy dissipation during the rocking due to local impact, and oops, everything has just disappeared. Thank you very much for your listening.
Thank you very much, Dina. Ending slightly abruptly there, but yes. You did a great job in distilling down 4 years of investigations into a 15-minute presentation. So thank you very much for that. And I'm pleased to say, let me just get this. No, I can't move that screen along. I'm pleased to say that. Okay. Thank you. So we are running to time, in fact, maybe even a minute early. But to prevent us from all suffering from deep vein thrombosis, we have built in a 10-minute tea break. So please feel free to get up, walk around, refresh your teacup, and we will reconvene at 3 o'clock when we're going to have 3 more very interesting presentations. I'm sure that William Alsop will keep us entertained with his coastal structures and sort of historical and engineering aspects Paul Taylor on the wind turbines, and sorry, my mind has gone blank. And of course Michelle Cusqua from Serema, so talking about the French lighthouses, and I'm hoping that you've got some of your very interesting footage in your presentation, Michelle. So we will start again at 3 o'clock promptly. So we'll see you again shortly.
You've had your teacup replenished.
Yes. It's full, thank you.
Very good. I can't show you mine.
Okay, so I make it 3 o'clock now. So welcome back, everybody. Next up is Professor William Alsop. Now, William Alsop is a, sorry, I have to excuse me reading from another screen. I am paying full attention. He founded William Alsop Consulting in 2017 after working at HR Wallingford for 48 years as Technical Director for Maritime Structures. He served on the Institution of Civil Engineers Maritime Board, PIANC working groups, and contributed to PIANC, BSI, ISO and ICE working groups. He's currently an honorary professor at University College London and currently completing a PhD on old British breakwaters at University of Edinburgh. And William is going to speak on predicting safety of old vertical walls, the development of understanding and prediction methods. So William, you're very welcome. Thank you for joining us this afternoon, and over to you.
Thank you, Alison. The first thing one has to do is remember to unmute your mic and find the right presentation and then full screen it. And I'm hoping that you can now. Right, I've changed my title slightly. I've simplified. I'm sticking with breakwaters rather than columns. One of the things that was interesting in conversations over the last year or so is just how recently we have developed prediction methods. It's sometimes quite surprising. I'll run through vertical wall types, talk a little bit about the history of wave load guidance, try and distinguish between quasi-static and impulsive. That's an artificial distinction, but we need to make it. There's some history in how to avoid impulsive loads. And then for my PhD, I've done so far 3 case studies, Wick, Alderney and Dover. On this occasion, being time limited, I'm just going to talk about Wick. For those who know the northeast of Scotland, if you go up to Wick, the breakwater I'm talking about is the one that is not there. Breakwaters have been built for many centuries. The interesting thing is that the Greeks designed harbours in places where you didn't need a breakwater. The Romans were much more awkward, but had better technology, and they designed harbours where you did need breakwaters. But those techniques didn't really transfer across to the UK. So generally breakwaters were built by building a large mound on the seabed and then building a blockwork wall above it. Except that that often didn't work so well. So this was a classic bit of technology that got lost. There was a long and complicated history, some of which appears in Pepys's diaries. But in 1670, late 1670s, 1680s, the British built caisson breakwater at Tangiers. They built wooden chests. They were so big that they were named as if they were ships, and they were towed all the way from southern England round to the North African coast. Anyone who sails and is aware of the prevailing winds across the Bay of Biscay and has any idea of how close to the wind you can sail a square-rigged sailing ship would clearly be horrified at the concept. But they did, and they towed the lower part. Ah, my mouse appears to work. So this would have been the box. This is top hamper added later, but these boxes were towed out from England and sunk onto a mound and then filled with a material called taras. It's not entirely clear what this is, but it's probably a vaguely cementitious baked earth, somewhat like laterite, I imagine. But that was filled, and they built the masonry tops. And then, of course, we concluded peace, so we abandoned the new harbour. Only, of course, the one thing you didn't do is leave the harbour to your erstwhile ally, who might then become your enemy. So we blew it up. And curiously, these were easier to remove than the original works of standard blockwork masonry. But nobody went back to those after that. We clearly felt we'd lost it. And the other thing that was very clear is that nobody had a clue of what the wave forces were. John Scott Russell, I mean, this is remarkably recent, 1847. Hard by the young engineer, you'd be left to guide entirely by circumstances. Reactive modelling, I'm sure there's a modern word for that. Shortly afterwards, Thomas Stevenson was also finding the frustration, and he then designed a machine to measure wave forces. A natty cast iron frame, a disc, the wave forces come and hit at this end. They push these rods back, and inside here there's a leather disc that's a friction fit on the rods, and the leather disc slides along the rods to a position equivalent to the biggest force as resisted by the springs inside. So you had to go out to the machine, you had to open the window, and you had to measure how far the leather disc had moved. And you needed to pre or post calibrate the device. Wave force prediction methods, I may have missed a few out, but in my book, the earliest one is Hiroi in Japan, and that would have been only published in Japanese. Saint-Flou publishes in French in 1928 and is remarkably good. You don't go too far wrong with Saint-Flou. Bagnold at Imperial, I think, did some experiments, and some of his guiding principles are still true. Minikin suffers from the fact that his formulae got translated wrongly and have led to the famous P max is 101, blah, 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 where 101 is pi times g. Let's see how many of you can work that one out. 1970s Ito, cited by Goda, a very simple formula, and one that's really pretty good. We then follow to the famous Yoshimi Goda in 1974, then published in English in 85, 2000 and 2010. Broken wave action as part of the Syria research project on sea walls. Blackmore and Hewson at Plymouth publish a method for broken waves. Goda revises his work in 85, and then Takahashi and a number of co-publishers write a series of papers on impulsive loads, essentially modifying GODA. It wasn't until 2001 when the Proverbs Research Project reported where we started to get a more logical steps in predicting. We still have Minikin being cited by the US Army Corps of Engineers, but wrongly. Moving on to impulsive waves, in the original research project within Proverbs, Kirsty McConnell, Diego Vichinanza, and I and others have proposed a number of simple impulsive load formulae. Giovanni Cuomo and co-researchers then took those results and some further research measured by Tom Bruce and I under VOWS, put those data together and came up with some revised methods. Okay, so putting all of that together, one would have thought that the loads on vertical walls were well known, but the truth is that horizontal forces have been better predicted, and certainly pulsating horizontal forces are pretty well predicted. Impulsive pressures less well, and I'll show a reason why those aren't awfully clear. Overtopping and downfall loads have a substantial effect on failing the upper parts of these structures, and were almost certainly the major reason for the collapse of the wall at Dawlish, where impulsive overtopping came over and blasted out the track bed, then allowing the front wall to be knocked off. What is very poorly known is the seaward forces. There was something in GODA, and there was a little hint in GODA's graphs that show that seaward loads could on occasions be bigger than the positive landward loads. An area in which there is virtually no knowledge at all is internal pressures. Although Gerald Muller and his team then at Belfast, and Adrian Pearson, Tom Bruce and I did some testing at Wallingford, supported by ICE, that at least identified outward movement of blocks.
2 minutes,
GODA
please,
had some, okay, get a move on. Right, GODA had some rules on when you ended up with impact loads. I then drew this diagram from that. What GODA didn't do is tell you how big the loads are if you got down here. The GODA level loads are down here at about 1 rho GHS. Impulsive loads were up here. This isn't the worst that Janice McKenna and I measured. We got up to about 40 times. These are enough to have moved structures backwards, and present design methods in Japan actually calculate displacement back. The updated rules in Proverbs are more complicated but more comprehensive. So the procedure that we outlined at the end of Proverbs and that I've been using for my case studies is calculate the waves subject to shoaling and breaking, then calculate a breaker classification on the mound, estimate a first version of the wave loads, improve it to GODA, then, and you always do that, whether you're likely to have impulsive loads or not. and then you calculate impulsive loads and or Blackmore-Hewson's broken loads. This illustrates the impossibility of a single impulsive load. At any exceedance probability, you could be anywhere on this envelope. So at Wick, this was the breakwater that Stevenson built. Notice the change of angle here. This is what happened to it. That's a broken end, completely swept away, and that's the outer part of the breakwater. If you go there now, this is the start of the breakwater, and yes, the end is out there somewhere. I think that buoy marks the outer end. 3 stages. Firstly, shoal the waves, then apply a breaking limit. Use Calabrese's method to calculate the percentage of breaking waves or impulsive waves. Get a first handle using ETA or Goda. ETA a bit more pessimistic, mostly. There we have the Goda loads, and then calculate factors of safety of sliding or overturning. It's quite pleasing, given that Wick breakwater has disappeared, to find that it does have factors of safety well below 1 for virtually all of it, except the route, and that's with a lower wave height than what we think probably did occur. So to conclude, the design methods were initially entirely on experience, and the formulae were really only available after Saint-Flour in 1928. And in truth, they weren't really available until close to the turn of the century. One should always calculate the momentum-based loads using Goda. Impulsive loads can be very much higher, but will be very much shorter. And to use the impulsive loads, you almost certainly need to take some sort of dynamic analysis. I've shown you the results for Wick. Those for Alderney and Dover are in a pair of upcoming papers in ICE Forensic Engineering. Thank you very much.
Thank you very much, William. Thank you. I think the presentation perfectly demonstrates the difficulties that engineers have in prescribing wave loads. So that was really helpful. Thank you. And we can take any questions at the end. So if you'd like to stop sharing your screen. And the next presenter is Professor Paul Taylor, who is currently a professor in the Oceans Graduate School at the University of Western Australia. But today is in the UK and has been in the UK for a few weeks now, I believe. So Paul will be presenting on towers without rocks, wave loads on offshore wind turbines. So we're just going to bring things right up to the modern day. So over to you, Paul.
Okay, thank you very much, Alison. Let's just hope so can you see my presentation?
We can see it, but not yet in full screen. I think it's trying to do it.
How about that?
There might be a delay, but yes, yeah, perfect.
Okay, good. Thank you very much for the introduction. It's a great pleasure to talk today. I want to talk about an easier problem than rock lighthouses or breakwaters. The problem where you have a tower without rocks. So the modern application is wave loads on offshore wind turbine support structures. And you can see the first slide with hundreds of these installed in different parts around the UK now. Oops. Oh, right, here we go. So the offshore wind is booming, as everybody knows, both around the UK and around the world. And this picture just shows a few development regions, mostly on the east coast of the UK, although some on the west coast. Number of offshore wind farms which are installed, planned, or consented for. So enormous numbers of fixed turbines coming. This slide shows how large offshore wind turbines can get compared to, for example, the Eddystone Lighthouse on the right-hand side. We are talking about towers as large as the Eiffel Tower. This being an American slide, most of the exemplar structures on the right are American, on the left are American. So you can buy a General Electric turbine for 12 megawatts now, absolutely enormous, but the support structure up to essentially the horizontal blue bar is essentially the same size as the Eddystone Lighthouse, which is an interesting statistic, I think. There are a whole variety of different concepts planned for both fixed and floating offshore wind, but I'm going to concentrate on the simplest, on the extreme left, of a single column, bottom-mounted column with the turbine mounted on top. In deeper water, you might go to a truss structure, and if you want to go even further offshore, you might go for floating. And one of the things that we're doing in Australia is doing a small amount of work on the responses of floating wind turbines. But I'm going to talk about fixed today. A few more pretty slides just showing how large these structures are. The small structure in the foreground is essentially the electricity substation, which is absolutely dwarfed by the towers. For fixed columns, there are various different types of foundation used. You might have a tripod with 3 corners piled into the seabed. You might use a suction gravity base type structure or other concepts, but they all have a single column coming up through the free surface. So the loads on them are predominantly close to the free surface, so they get similar wave loads. I want to talk about some work that we first presented a couple of years ago in a Journal of Fluid Mechanics paper, based on experimental work done at DHI in Denmark several years prior to that, where we examined in some detail the fluid loading and the induced forces on single isolated columns. The concept for this is we're going to look at smooth loads, which are essentially relatively easy to analyze, to understand, and then also some slam loads at the end. So let's start off with the expansion for a regular wave, a so-called Stokes wave expansion. And you can see the top formula here, 3.1. We have a component, cos theta, the normal linear component. We have a double frequency and triple frequency component, and you can go as high or amplitude here, non-dimensionalized by the radius. And each term has a nonlinear coefficient on it called, in this case, SEE2, for example, which describes the interactions at second order for elevation, hence E, multiplying the A upon R, the non-dimensional size of the wave, and then the cos 2 theta function being the time variation. We can generalize this regular wave solution into what happens if you have an irregular wave train by simply replacing cos theta by essentially a linear narrow-banded process I'm going to call eta 1. Then if you want a double angle, so cos 2 theta is cos squared minus sine squared, so that simply becomes eta 1 squared minus eta 1 Hilbert squared, and the Hilbert transform does the 90-degree phase shift. And that turns out to work really quite well for regular waves, and irregular waves, which are non-breaking. We're going to try and do the same type of expansion for the force time history, the smooth force time history. So I'm going to break that down into a linear component, a double frequency component, a triple frequency component, etc. Non-dimensionalized via the groove formulation for loads on columns. And little curly F1 in the brackets is the time history structure. The large capital F1 is the magnitude of the force. So that we have a double frequency component, You can see an F1 squared minus F1 Hilbert squared, which is essentially cos 2 theta. But because for forces, there are phase shifts, we have to have an alpha and a beta as phase functions as well. But essentially, we can create a double frequency signal from a linear component and a triple frequency signal from 3 products of the linear components. Let's see if that actually works. So what we have here are instant waves on the left and force time histories on the right, Stokes expansions running from top to bottom. So the linear component contains all the main energy transporting information. We get a second order set down term, a double frequency term, a triple frequency term, etc., as high as you want to go. And that works very nicely for the instant waves. But one can also do it for the force induced by a wave group, which is shown on the right. Linear, double frequency, triple frequency, and so on, with a small second order difference term as well. So the idea of a Stokes expansion seems to work really quite well for waves and for forces. You can, if you want to show off, go to higher order than that. Here's an expansion up to roughly 12th order, showing that the Stokes expansions work pretty well all the way up as far as the data is accurate. We can test the focus as we did previously. The large case on the right, the small case on the left, and you can see the forces for the 2 cases, the crest and the trough focus groups. The factors 1.73 times show the ratio of the linear signal for the small case to the large case. If the theory is working, each of the harmonics should simply scale as this factor to the relevant power. So the 4th harmonic should be 1.73 to the 4th. And the 2 graphs either side are plotted so that they should look the same for the small case and the large case, as indeed they pretty much do all the way up, curiously, apart from the 3rd harmonic, which occasionally shows some odd structure. But the basic idea is that we can describe all the harmonic structure for the forcing in terms of the linear time history, which is easy enough to calculate. One can check that, and we've done a lot of testing on both a flat bed and a sloping bed at DHI. The linear force component should match linear diffraction theory, which does very nicely, as you can see on the left-hand side. And even Morrison, with a simple inertia coefficient of 2, works quite well if the cylinder is not too fat. On the right-hand side, the second order sum term, the double frequency forcing, again reproduces the experiments really quite well, using a second order diffraction code, the Oxford diffract code. So we can conclude that linear and second order theory works well. There's little drag. We're in a regime where the cylinder size and the wave amplitude are comparable, so that we're in essentially a small body but violent diffraction regime. And essentially there's no well-established theory beyond second order. There's some theory of 3rd, but nothing beyond that. But the decomposition in terms of linear signal to the relevant power seems to work quite well. Let's try and build approximations. So we've done that here for the 2nd, 3rd, 4th, and 5th harmonics. Everything is based on the linear signal, the 3rd one down. The total of the measured force time history is at the top. And you can see the 2nd harmonic sum, the 3rd, 4th, and 5th. Underneath the red curve is a dashed blue curve for the harmonics, which is their reproduction using simply powers of the linear component. And you can see that works really very nicely for this case. So to summarize, we do a Stokes expansion in terms of force. For the nonlinear harmonics, we have an amplitude coefficient, the S, F, F, N components, and we have a phase coefficient, which essentially just gives a phase shift compared to the linear crest. These coefficients only are dimensionalized in terms of wave frequency. So this is a fairly robust description. There's other complications that one should include for cylinders, and this is beginning to look more like the Lighthouse case. The slam loads turn out to can be significant depending on the violence of the breaker. and their structural dynamics. And you can see on the right-hand side here a case of the force transmitted into the foundation due to a crest focus wave group hitting a column, where the resonant frequency of the structure is about 4 times that of the wave. So substantial structural dynamics with the largest response into the foundation, the swing back rather than the applied load in the wave propagation direction. Slam loads are associated with impacts on the front of the column, so a violent
2 minutes,
fluid
please,
sheet
Paul.
thrown up the front. And a couple of nice photos from quite an old paper by John Chaplin, Rainy and Yen, published in JFM. So to summarize, I'm suggesting it's possible to do a decomposition for the horizontal loads and moments in irregular ways on a surface piercing column. This works well for smooth load components for which the Stokes expansion for the harmonics can be produced. So the harmonics are simple nonlinear functions of the linear component, but there is a suggestion of a little bit of extra physics at third order, which may be related to the FNV ringing model. We need a model for additional slam loads, which we're presently working on. And the ultimate aim is to produce a simple design recipe for wave loads and offshore wind columns, wind turbine columns. You're not going to have the time or computer power to do a CFD calculation for each column as you change the wave properties a little bit. I'd like to acknowledge my co-workers on this, particularly Jun Zhang at Bath and Tom Adcock in Oxford, Li Fen in UWA now, was in Bath, and Samar Rays that we've had in Oxford, and many others. Thank you very much. I'll finish at that point.
Thank you very much, Paul. Your presentation was a very nice balance to William Alsop's empirical equations to have the theoretical aspects as well. So thank you very much for joining us this afternoon. Okay, and then our final presenter this afternoon, we have Michel Kusker, who's been working for 15 years at CERAMA. CERAMA is the technical partner for the French Aids to Navigation authorities. He's currently the Maritime Safety Project Manager and has also been the Vice Chairman of the IALA Engineering Committee since 2018. So Michel, over to you, please.
Thank you very much, Alison. I'm trying to share my screen. Can you see it?
Yes, thank you.
So thank you very much, yes, for this kind introduction and also for the invitation to this workshop. I'm going to present how French Aids to Navigation Administration has been working with the scientific community on 2 lighthouses since a few years. Nicolas Fadi should have done this presentation, but he was not very comfortable with the use of the virtual meeting, the idea of virtual meeting. So he asked me to do it. So it's my pleasure. So before getting to the heart of the matter, let me give you some background on French lighthouses. And as you will see all along this presentation, it's quite the same story than in the United Kingdom, as it was brightly presented by all the previous speakers. A bit of French history. Then, thanks to Augustin Fresnel and his invention, the lens, France started to light its coast in a national program conducted during most of the 19th century. It concerned 51 lighthouses which were built during this period. Today, matching with the IALA definition of a lighthouse, there are 139 of them in France, including overseas French areas. 47 of them are fitted on the open sea. And even if they had been built more than 100 years ago, they mainly don't show worrying signs of structural deterioration, except some of them, and we are just going to talk about this one. So a few words first on the French Aids to Navigation organization. The management of French lighthouses is the responsibility of the Ministry of Ecology and Transport. We can compare that to Trinity House, as it was presented by Rob previously. CEREMA, as you said, Alison, during your introduction, is the technical partner of the Ministry for studies, development of methodologies, capitalization of best practices, and innovation or research on all the skills related to aids to navigation, including, of course, civil engineering. Sometimes we develop partnership with academic or industrial laboratories to go further because, as an African proverb says, alone you go faster, but together you go further. And the two cases I'm just going to talk about are a good example of such a partnership. Let me introduce our first case study, La Jument. La Jument is located in Brittany, close from Brest in Ushant Island area. It is one of the most famous French lighthouses, thanks to many spectacular pictures of it. It was built on the beginning of the 19,000, and it is representative of the sea constructions made at this time, with maybe low knowledge of masonry dynamic behavior or on swell. And the top picture shows quite well what were the conditions for workers at this time. So it needed successive reinforcement until 1935, and today it has some trouble. We can see degradation, as you can see on the down picture, on the basement, which have been urged by extreme storms recently. And we have some doubts also on the residual effectiveness of the repairs carried out almost a century ago. On this slide, you can see some pictures of lighthouse keepers take over, and it's not so old pictures, maybe 10 years ago. It's very spectacular, of course, and dangerous also because of the absence of dock. If the project needed, we can provide later some videos, if you want, of the takeover on this lighthouse. So take a look now at what we did with the scientific community on this structure. First, we initially took an opportunity to work with EPFL, École Polytechnique Fédérale de Lausanne in Switzerland, and especially with Emmanuel Denarier on the structural behavior of the lighthouse. In 2014, we previously had worked with him on a different project using high-performance fiber reinforced concrete to reinforce some aids to navigation. He made a 3D modeling of the structure using historical data, plans, which were valuable. And this work helped us a lot to propose some solutions to reinforce the basement of the lighthouse. But this solution no longer had been conditioned at this time, because then we moved to a second approach in order to work on the dynamic behavior of the lighthouse. And since 2017, we have been working on two aspects. First, characterizing swell on site. And as you can see on the pictures, we need to characterize the swell on this side especially. And we did that through a partnership which had been developed for that purpose with academic, France Énergie Marine, and other institutes as Ifremer and CHOM, which is our hydrographic institute. The aim is to identify the efforts due to the wave on the structure. And we have been using for that different sensors, radar, wave buoys, and also stereo camera. In parallel, we installed some accelerometers on the lighthouse to measure its response under efforts. And the idea, of course, is to cross those data to link the effect of the waves with the degradation of the lighthouse. Here you can see a record from the stereo cameras, which give a good idea of the elevation of the wave on the site, more than 10 or 12 meters between top and down, or blue and yellow. And now, where are we now? All the instrumentations had been deployed, and we recorded a significant event in January 2018. Besides, with the help of Professor Alison Raby, we published some short article on that experience on the publication you can see on the slide. And since we improved the instrumentation by adding more sensors, including pressure sensor, no result to share at this time because of the impossibility to go to the site by now, and we will have to wait for the end of the lockdown to go back there. Our second case study is L'Île Vierge Lighthouse. L'Île Vierge, that means Virgin Island. And it was built at the same period than the previous one, and is known as the higher lighthouse in Europe, which is 82 meters high. It's close to Brest also. The aim we try to achieve on this lighthouse is different from the previous one. We detected a network of cracks at the base of the lantern a few years ago, and one of them is visible on the right picture. We first thought that the cracks should be due to the corrosion of the steel frame inserted into the stone. It is a phenomenon that we encountered on several other lighthouses previously. But when we disassembled the frame, there were no trace of corrosion on this part of steel. So we started to work in order to find another explanation before fixing the cracks. We then contacted an academic laboratory at the National Institute of Applied Sciences, INSA, in Toulouse. They launched a thesis on the topic, which is called Development of a Diagnostic Methodology for Masonry Lighthouses. And Louisa Pena, the PhD, supervised by Nathalie Domed, made some archives researches, and then we monitored the lighthouse with different sensors as crack meters that you can see on the top picture. She also made some tests on laboratory, on stone, for example, and she finally worked on a 3D modeling of the lighthouse. The thesis will be defended by a couple of months, and some conclusion can be shared today. As we already know, it is not a corrosion problem. It seems that it is not either an effect from the wind on the tower of the lighthouse. And according in particular to extensiometers that you can see on the down picture, circled in red, the cracks seem to come from the thermal actions caused by the lantern, that we can say greenhouse effect. So this is the end of my presentation. For more detail, please contact either Nicolas Fadi or me. You'll find our contact details on this final slide, and I will provide this presentation to Alison and Yves. Thank you very much for your attention.
Thank you so much, Michel. Thank you very much for an excellent presentation. And we also acknowledge Nicolas Fadi in the wings as well, who has been working on various aspects of this research over the years. And I've met Nicolas on a couple of different occasions. It's also interesting to see you presenting the work from Île Vierge, and Nathalie Domed was able to spend some time at Plymouth and UCL last summer, I think it was, or maybe the summer before, and we talked about the modelling of that lighthouse. So it's really great that just coincidentally we've been working on very similar topics in parallel, and from time to time we've been able to overlap and encourage each other and share some of the struggles and some of the successes of working with these amazing structures. So thank you, Michel, very much. Okay, so we've come to the end of the formal presentations. Thank you all very much for staying this far on to a virtual workshop. Okay, so drawing things to a conclusion then, we hope to have future meetings to discuss details of any forthcoming proposals that we'll put together. We are aware who's joined the webinar, so you might get contacted by us. If you want to ensure that you're included in future discussions, then perhaps if you could drop Eve Allen an email to make sure that we have got your details. It just remains for me to give a huge thank you to our panelists. It's quite an ask to produce one of these virtual presentations. So thank you so much for joining us. Thank you for spending the time putting the presentations together and also coping with the nerves of presenting over the internet. So thank you so much. And for also engaging with the discussion that we've just had. And thank you to everybody who has joined the workshop this afternoon. It's a pity we can't sort of find out sort of face to face who everybody is and what their interests are. But do keep in touch. Primarily through Eve Allen or for myself, Alison Raby. You'll find me if you just Google Alison Raby, University of Plymouth. Okay, so thanks very much for your time this afternoon. Thank you for engaging with what we think is a very exciting topic, and for making the end of the STORMLAMP project to be a really enjoyable experience. So thank you to everybody. Thank you. Goodbye.
Thank you. Thank you for participating. Bye-bye.
Thank you and goodbye.
Thanks all.
Yeah, thank you, Alison. Bye for now.
Yeah, thanks very much.
So I will stop the recording now, Alison.
Okay, thanks, Dina.